Hello, my name is Neil Hyatt from the University of Sheffield in the United Kingdom. And in this video tutorial, I'm going to take you through some of the functionality of the Hermes software for pre-processing of laboratory X-ray absorption spectroscopy data. The Hermes software is accompanied by a comprehensive user guide, and I encourage you to refer to this as we go through the tutorial. It also contains instructions for downloading and installing the Hermes software. So to download and install the Hermes software, simply navigate to GitHub and then to the folder /XAS Sheffield, as you see here. Click on the Hermes repository, and on the right-hand side here with initial version latest, and you'll see that you can download an executable file and also the source code. So if you're not a coder, the executable file is probably the most appropriate for you, and you can see that it will download here on the right-hand side. So once you're ready to begin working with Hermes, simply place it in an appropriate directory and double-click on the executable. What you'll see then is that Hermes begins to launch its installation procedure. So just click yes. You'll see then Hermes begins its extraction, and once complete, it presents the Hermes dashboard. Okay, so here we have the Hermes dashboard. You can see that there are a number of tabs shown here along the top, and Hermes encourages you to work in a logical fashion from left to right through these tabs. So the first is the data input tab, where you can load your data in and work with it using the tools here at the bottom that I'll go through shortly. The next is the absorption tab, where you can plot your data as absorption using component I0 and IT data files, and also write that as a separate data file. The energy correction tab, where you can calibrate the energy scale of your data to get it onto the true energy scale. The About tab tells you about the development of Hermes, and then the License tab gives you the licensing conditions for use of the software. So let's begin with the Data Input tab. You can see here that there are 4 workspaces. Workspace for I0 and IT, because with Rowland circle spectrometers, one typically acquires data with the sample and without the sample, and you need to combine those data sets into one file to, for example, work with in Athena. We also have workspaces for I0 leakage and IT leakage, again collected with the sample and without the sample, with a large detector offset. And sometimes the leakage correction can be important depending on the characteristics of your sample, the monochromator, and your spectrum. So the leakage effects are covered in detail in the Hermes user guide, and we'll be working through our examples, assuming that we need to correct our data for leakage effects. Okay, so down here at the bottom, you can see that we have a drop-down menu. And depending on which of the workspaces we select in here, this controls into which workspace we will load the data or use the tools below in order to work with it. So we'll simply begin by selecting the I0 data, click Load Data Files, put in the path of your data, and we want I0 data. You can see here I have 8 data files. I'll load them all in together. And what you're presented with at the first occasion that you load data into Hermes is this dialog box, which requires you to map the required data columns, energy theta counts, ICR and OCR, to the correct columns in your data. Okay, so in this case, energy simply maps to energy, theta to theta, counts in this case is counts per live, ICR to ICR, and OCR to OCR. Okay, so ICR and OCR allow you to make a dead time correction to the data automatically, and this is covered in more detail in the user guide. Okay, so having adequately mapped our columns, we simply click OK, and you'll see that the data is loaded here into the Hermes workspace. So we can now repeat the process for IT data. Load files, choose IT. I0 leakage. And IT leakage. Okay, so that all looks good. If you make a mistake, and for example, let's say you load into the I0 workspace data from which are IT, you can simply remove that by clicking on the data file to highlight it and clicking Reset Selected. And that will remove the data file. If you click Reset Data, then this will ask you if you want to clear all the loaded files in the workspace highlighted here in the drop-down menu, in this case, I0. So if you click yes to this, all of these data will be removed. So in this case, we'll click Cancel. You can also reset all data, in which case it will clear all the data in all the workspace. Good. So typically the first thing you'll want to do when you load your data in is to plot it, to inspect it. And Hermes provides a number of options for doing that. So let's begin by looking at some IT data. Okay, so if we select one data file and hit Plot Selected Graphs, then it will simply produce the one data file. If you select all of the data and hit Plot Selected Graphs, then it shows you each data set in its own individual panel, which is useful for inspecting them individually. You can also produce a stacked plot simply by clicking this checkbox here. And now with the offset at 0, clicking Plot Selected Graphs in this case, with all the data highlighted, which would produce a plot with the data all superimposed. So this is quite good for comparison. Okay. If we add an offset to this box, so let's say 200, again with the stacked plot box ticked, clicking Plot Selected Graphs now gives you a stack plot of the data displaced along the y-axis by 200 units. So again, this is quite useful for scan-to-scan comparison. Okay, so the next thing you'll probably want to do is to merge several data sets to produce a single data file. So to do this, simply select all the data files in the workspace, so again with IT. So in this case, clicking Control-A, or with Shift down 1 to 8, we'll select all the data files. And you can also, for example, if you wanted to only integrate certain data files, merge certain data files, you hold Control down and click the files that you want to select. Okay, but in this case, we want to merge them all, so Control-A is good enough, and generate data merge. Okay, so in this case, we're asked to enter a file name because the merge file will be written to its own data file. So we'll call it UTA. So I'm just going to call it, in this case, IT. Okay. And then you can put in a header. So you could put something in here about the sample name or the conditions under which the data were collected. For example, the tube kV milliamps. But in this case, I'll just give it a shorthand of IT UTA 00. Okay. And you'll see now that this file has appeared within the IT workspace. Okay, so we can plot that, and we'll compare it in this case to just one data set, and hitting plot graphs. In this case, because I've clicked off, the stack plot shows them side by side, but you can see obviously the signal to noise has been improved on the merged data. We go to stack plot with offset of 0 and plot again. Now we'll see them superimposed. And again, you can see the improved signal to noise here of the IT data, which has been merged in red. Okay, so if we repeat that process now for the I0 data, so remember to change the measurement type, in this case to I0. Okay, so select all, generate data merge, so I0 UTA 00. Okay, and again, we can plot those and compare. And so, yes, again, as you would expect, the merged data here, I0 in red, again, improves signal to noise over the individual data set. We'll repeat that for the leakage. So remember to change the drop-down menu here to I0 leakage, generate data merge. So I0 leakage, UTA 00. And then the IT leakage. Okay, good. So again, we can compare, if we look at the I0 leakage, the merged data with a single data set. And that's actually I0 because I haven't changed the measurement type here. So I0 leakage. Okay, and once again, you can see improved signal to noise in the merged data. Okay, so Hermes also provides the functionality to generate a polynomial fit, and that can be useful if your data are smoothly varying. Plotting a polynomial fit will eliminate the addition of Poisson noise to your computed absorption data. So in this case, if we look at I0, the merged I0 data, sorry, that's the leakage, I0. You can see that we have a number of emission lines in the data, and it's going to be very difficult, impossible in fact, to fit those adequately using a polynomial function. So in this case, I prefer to normalize the data simply using the measured I0. In the case of the leakage data, however, you can see that this is smoothly varying, and so that's more appropriate clearly for fitting a polynomial. Okay, so to try and fit a polynomial, okay, we choose the measurement type, in this case I0 leakage, highlight the data file that we want to work with. So in this case, I'll take the merge data file and specify the polynomial degree. So for data of this character, a third order polynomial should be sufficient. Okay, so if we generate polynomial fit, you'll be asked for a file name to save the polynomial fit data. So I'll call this I0 leakage P3. And then you'll see that that file's been created. And if we now compare these, so a stack plot with 0 offset will superimpose those data. You can see here the fitted polynomial in red. And so in this case, it would be appropriate to work with that if you prefer. And it's advantageous because, clearly, as I said, it avoids adding additional Poisson noise to your computed absorption data. So we can repeat that exercise for the IT leakage. So change here to IT leakage in the measurement type, generate polynomial fit. Okay, so order 3 again. And if we compare these two, plot selected graphs with IT leakage highlighted, stack plot 0 offset. So again, they'll be superimposed. You can see the result. Okay. So that's really the conclusion of the pre-processing of the data in the data input tab. So we're now ready to use our pre-processed data to compute the absorption. So we'll click now on the absorption tab. So in the case of the absorption tab, you can see that initially it presents to you just two workspaces, I0 and IT. If you want to make a leakage correction, you need to click this tick box at the bottom, in which case it will give you all four workspaces in order to correct the data for leakage. So I'm going to proceed with a leakage correction in this case because for our data it's important, but you would follow a very similar procedure with this tick box unchecked, simply to process the data without leakage correction. Okay. So to process to plot the absorption, you need to click one I0 and one IT file. So of course we use the merge data, but in fact you could pick any pair of these that you wish. That would also be okay. But clearly in this case it makes sense to use the merge data. And so if leakage correction was not to be made, you could now plot absorption. In this case, because the leakage is significant, we need to click also two leakage data files, one for I0 and one for IT. And in this case, we'll use the polynomials because, as we've discussed, they don't add additional Poisson noise to the computed data. Okay, so if we now click plot absorption, you'll see that we get a nice plot of absorption versus energy. And if you're familiar with actinide chemistry, you'll recognize this as the uranium L3 absorption edge. And so the data are plotted as a function of energy and also as a function of theta here on the right-hand side. And these look very nice. So you can also, as I said, choose to plot just individual data sets. And in this case, of course, you get data which has considerably more signal to noise, considerably less poorer signal to noise ratio. Okay. So again, if we choose our preferred data sets, and this time click, so plot absorption once again gives us the absorption as a function of energy and theta. If we now click generate absorption file, and I'll just click over here to copy the path where I want to put these data. So enter a file header. So I'll call this UTA, which is this particular sample name, 00. And where you are, and then you have to tell it where you want to save the data. It will then remember this path. So I'll just put it here in the main data folder. So choose a file name. So I'll just call it UTA00, which is the sample ID. Click save. It will then tell you that it's successfully written a .dat and a .list file to your preferred folder. Okay, so click OK. So if we look here on the right-hand side, you can see it's successfully written these two files, uta00.dat, uta00.text. So if we open the .dat file first of all, and I'll just maximize it, you can see that up here you've got the header, which I gave the data, and then columns of energy. So this is theta, the computed absorption, I0, IT. You then have I0 minus I0 leakage, IT minus IT leakage, I0 leakage, and IT leakage. So the component data files that you use to produce the absorption in this case. Okay, so the I0 and the IT will be the merged data files in this case to give you the counts, and similarly for the I0 leakage and IT leakage, these will be the counts determined by the polynomial fitting. Okay, so if I close that and then show you the text file here. So the text file basically kind of incorporates all of the file names and headers that you have used to compute the absorption in this case. So you have the I0 file, which was UTA00, the IT, the I0 leakage, which in this case was a polynomial fit of third order. So it gives you the fitted polynomial coefficients, and similarly for the IT leakage. So this text file allows you essentially to maintain curation of your data by reminding you of which data files you used to combine to produce the absorption. Okay, so it's probably worthwhile mentioning at this point then, perhaps I should have done it before, if you go to the files where you had your original data, you'll see in each one we've got the data file that we wrote by merging the 8 individual I0 files in this case. So again, if we click the DAT file, okay, you've got energy, theta, and then you've got the merged counts per live, and these will be dead time corrected as discussed in the user guide. And in this case, the text file summarizes, it gives you, let's see here, what have we got? So we've got the individual file name of each data file. We've got the header from each data file. So there are 8 of those. And at the top is the data file that was written. Okay, so again, allows you to keep good curation of your data by reminding you of which data were integrated to give a particular data file. You know, personally, I find that very helpful. So if you look at IT, you can see that we have the same thing. If we look at I0 leakage, okay, so here we have the two data files. So we have the data file from the merge. We have the text file, which is the curation file, as I've talked to you. We also have one extra, which is the data file produced from the polynomial fitting. Okay, in this case, you've got the polynomial coefficients that were fitted at the top here. So it gives you the equation for the polynomial, and again, columns of energy, theta, and in this case, calculated counts per live. Okay. So if we return to the absorption tab, then what we've successfully managed to do now is to produce an integrated data file that contains our merged I0 IT and polynomial fitted merged I0 leakage and IT leakage data all in one data file. So the next step then is to perform an energy correction on these data using the energy correction tab. Now you can see that in the energy correction workspace, we have only one data file to work with because we've only produced one absorption file. So what you'll notice then is that as you work through these tabs from left to right, the data is pulled through. Okay, so you can't load in a previously worked on or calculated absorption file into this space. You have to calculate it each time, but as you've seen, once you get used to it, that will be a relatively quick process. So to initiate the calibration, we click on our absorption data file, which we produced in the previous tab. And actually what we have to do first is choose the file to define the characteristic monochromator energy. So if we highlight this file and click at the top here, choose file, you can see that now these values of theta and energy are populated. And so what Hermes has done is to go to this absorption data file and pick the first value of theta and the first value of energy from which to calculate the characteristic monochromator energy. And this is dealt with in more detail in the user guide. So I'll encourage you to refer to that rather than explain it here. So it's probably worth explaining a little bit about how the energy calibration works. So Hermes requires you to have a reference data set for which you have determined the observed and true energy of a particular feature in the data. Okay, so in this case, our reference data set is a sample of uranium oxide, UO2, and we acquired data on that sample, both on the laboratory spectrometer and also on a calibrated synchrotron beamline, so calibrated with an yttrium foil. And we analyzed that data using the Athena software, and we determined the energy associated with the maximum in the first derivative of the absorption data. And so for the data acquired on the calibrated synchrotron beamline, that gives us the true energy, which is 17,169.21 electron volts, and the observed energy on our laboratory spectrometer for the same sample, 17,157.50 electron volts. So you could equally use, for example, a metal foil data set, and if you have reference data for that, the choice of reference compound is up to you. So then in initiating the calibration, Hermes tells you the calculated characteristic monochromator energy from the values that were picked from the data file. It then asks you to enter the observed energy for your feature of choice. So in this case, it's 17157.50 electron volts, and then the true energy 17169.21 electron volts. It then asks you for a file name for the corrected data. So in this case, I'll just give it the same file name, UTA00. And you'll see then Hermes tells you the theta shift in degrees, which is minus 0.180864 degrees in this case. So this is calculated from the specified values of the observed and true energy for the feature that we've chosen. Hermes then calculates from the characteristic monochromator energy the equivalent values of theta for the observed and the true energy. So observed and true theta values. And the difference between these is the theta shift, which is then applied to all the theta values in your data set. So that gives you a corrected theta scale, which again, using the characteristic monochromator energy, can then be transformed into the corrected energy scale. So again, more details on that are given in the user guide. So at the end of the calibration procedure, you can see that we're presented with two plots, so one in theta space and one in energy space. So these plots have a zoom functionality, which I haven't mentioned yet. So you can zoom in and you can see whether the calibration procedure has produced a sensible outcome. And in this case, it has. So you can see the result of the theta shift on the energy values and, sorry, on the theta values, and then also on the computed energy values. So the point here, of course, is that there's a non-linear relationship between theta and energy. So the calibration has to be performed in theta space by applying the theta shift and then transforming to the energy scale using the characteristic monochromator energy. And so you can see these plots look fine. So if you want to unzoom a plot, you can simply go to auto range, both axes, and then it will zoom out for you. And there's also the functionality to save a plot and so on. You can change the details and the plotting defaults in the properties menu. But I'll leave you to explore that on your own. Okay, so on the right-hand side here now in our data folder, you can see that we've produced two new files. And so we have the same file name and it's now underscore core, so for corrected data, .dat, and UTA underscore core, a text file, which I'll come to in a moment. Okay, so if we go to the corrected data file, first of all, you can see that we have all the familiar values that we would expect. Okay, so plus a few more. So working from the left, we have energy, theta, corrected counts, absorption, I0, IT, the corresponding values corrected for leakage. And then you can see I0, IT leakage. And then we have two additional columns. So we have the corrected energy values for the energy scale and also the corrected theta values. Okay, and so if we compare these values, so 16934.0, 16941.4, so you can see that there's a very significant energy miscalibration, a 0-point error in the spectrometer to be corrected for. And then similarly here for the two theta values. So the final data file in this case contains all the component data for you to work with and be able to plot in Athena if you choose to. So if we close that and then open the this text file, again, this is provided to assist you with data curation. So you can see that we have the calibration data file name, we have the calibration energy and calibration theta that were picked from this data file, the characteristic monochromator energy, the observed and true energies of the feature that we use to derive these values from our reference compound, and then the computed theta shift. So again, this is provided to assist your data curation. So if we go back to the corrected data file just for a moment. So when importing into Athena, what you'll want to set as your reference columns, or your data columns in this case, are the corrected energy scale. So this one here, so energy corrected. Your I0 will be I0 minus I0 leakage. So that's this one here. So I0 data merged and corrected for leakage, which we've modeled, remember, using a third order polynomial. And your IT leakage data, your IT minus IT leakage data. So your IT corrected for leakage, again, merged IT, subtracted from which is the polynomial modeled IT leakage data. Okay, so yeah, just to summarize again, in Athena, your energy column would be energy values corrected, of course, and then I0 would be I0 minus I0 leakage, and IT would be IT minus IT leakage. So that about concludes this tutorial. I hope you find the functionality of Hermes useful for your research. We've certainly found that it's reduced our error rate in data pre-processing, and yeah, I hope you have many happy hours of using it. So if you have comments or suggestions on the software, please send them in via the GitHub site, and that's all for now. Thanks for watching.